For centuries, we looked up at the night sky and saw a graveyard. We saw the moon, a desolate gray wasteland where dust remains undisturbed for millions of years. We saw Jupiter and Saturn, gas giants swirling in a cold radioactive void. The consensus was absolute. Earth was a miracle, a lone blue marble in a universe of dry, dead rock. We were wrong. The solar system is not a desert. It is drenched, hidden beneath miles of crushing ice, tucked away in craters that have never seen the sun, and erupting in violent geysers into the vacuum of space. Water is everywhere, and where there is water, there is the potential for something else, something that changes the math of our existence. We are currently standing on the precipice of a discovery that will rewrite history. We have moved from asking if water exists beyond Earth to asking how we can harvest it to fuel our expansion and what might be swimming in the dark oceans of the outer solar system. This is the story of that search. From the shadowed poles of our own moon to the alien depths of Europa, we are hunting for the most valuable resource in the universe. And the deeper we look, the more it seems that the solar system isn't waiting for us to bring life to it. It might already be there. The deception began with the moon. When the Apollo astronauts returned in the late 1960s, the samples they brought back were drier than the Gobi Desert. The scientific verdict was swift and brutal. The moon was a dry rock. It was a fossil of a planetary collision, baked by the sun and devoid of volatiles. For decades, this discouraged any serious talk of colonization. Why go back to a place with no resources? But we weren't looking in the right places. The moon has a secret. Because its axis is tilted only 1.5 degrees, the sun never rises high enough to illuminate the floors of deep craters at the north and south poles. These occupy a unique place in our solar system, permanently shadowed regions. In these traps, temperatures plunge to minus 250 degrees Celsius, colder than the surface of Pluto. Any water molecule that wanders into these shadows, whether from a comet impact or solar wind interactions, freezes instantly. And because the sun never touches it, it never melts. It never evaporates. It just sits there, accumulating for billions of years. The paradigm shift happened when we stopped looking with astronaut eyes and started looking with robotic sensors. The Clementine mission in the 90s gave us a hint, but the definitive proof came with violence. In 2009, NASA's L-Cross mission deliberately crashed a rocket stage into the crater Cabeus near the South Pole. It wasn't an accident, it was an excavation. The impact threw up a plume of debris miles high, and as instruments analyzed the dust in the sunlight, they found the signature we had been hunting for. Water, lots of it. We now estimate there could be over 600 million metric tons of water ice distributed across the lunar poles. This changes everything. To a spacefaring civilization, water is more valuable than gold. It is heavy to launch from Earth, but if you can find it in space, you have the master key to the solar system. Split water molecules and you get oxygen for breathing. Keep splitting them and you get hydrogen, rocket fuel. The lunar poles are not just scientific curiosities. They are the gas stations of the future. This realization has triggered a quiet, high-stakes arms race. Nations are no longer just planting flags. They are targeting these specific craters, aiming to control the most strategic real estate off-planet. But while the moon offers resources, it likely doesn't offer life. For that, we have to go much, much further out. And to prepare for that journey, we first had to go down. To understand the oceans of alien worlds, NASA had to turn its gaze away from the stars and toward the crushing depths of Earth's own oceans. There is a profound connection between the bottom of our sea and the moons of Jupiter. Both are high-pressure, lightless environments where survival seems impossible. Yet when we explore the Mariana Trench or the hydrothermal vents of the Atlantic, we don't find a barren wasteland. We find life. We find colonies of tube worms, ghost crabs, and bioluminescent predators thriving in absolute darkness, fueled not by photosynthesis from the sun, but by chemosynthesis, energy derived from chemical reactions in the planet's crust. This discovery on Earth validated a theory that had been borderline science fiction, that life does not need a Goldilocks zone near a star. It just needs water, heat, and chemistry. Today, Earth's oceans serve as the proving ground for our most advanced extraterrestrial technology. NASA and other agencies are testing autonomous drones in these depths right now. These aren't just submarines. They are artificial intelligences designed to operate without human input. When a probe eventually reaches a moon, like Europa, it will be too far away for real-time control. The radio delay would be nearly an hour. If a drone encounters a problem, it cannot wait for a human to tell it what to do. It must think. It must navigate jagged ice, sense thermal currents, and hunt for biosignatures on its own. We are building these machines to penetrate ice shells kilometers thick. We are teaching them to swim, and we know exactly where we want to send them. Beyond the asteroid belt, the solar system changes. The heat of the sun fades, and water no longer exists as a gas or liquid on the surface. It freezes into rock-hard ice. For a long time, we thought the moons of Saturn and Jupiter were just frozen snowballs, dead, static, and uninteresting. But when the Voyager probes flew past, and later when Cassini and Galileo arrived, they saw something that shouldn't exist. They saw cracks. They saw surfaces that were smooth, devoid of impact craters, implying that the skin of these moons was young and constantly recycling itself. And then on Saturn's tiny moon, Enceladus, we saw the impossible. Enceladus is barely the width of the United Kingdom, yet it is the most geologically active object in the outer solar system. At its south pole, through fissure lines called tiger stripes, this moon is vomiting its insides out into space. Massive geysers of water vapor, ice crystals, and organic compounds shoot hundreds of miles up, creating a glowing halo that actually forms one of Saturn's rings. This was the smoking gun. Enceladus isn't solid ice. It has a global liquid ocean beneath its shell, kept warm by the immense tidal gravity of Saturn pushing and pulling on the moon's core. We didn't even have to land to test it. The Cassini probe flew directly through these plumes, tasting the spray. It found salts. It found silica, which only forms when hot water touches rock, and it found complex organics. Enceladus has all the ingredients: liquid water, a heat source, and organic chemistry. Then there is the prize, Europa, Jupiter's moon. Europa is the giant of this story. It holds twice as much liquid water as all of Earth's oceans combined. Its surface is a chaotic map of red fractures, where the ice shell has cracked and refrozen, stained by salts from below. Unlike Enceladus, Europa's ocean is trapped beneath a much thicker crust, perhaps 10 to 15 miles deep. But the evidence suggests this ocean is in direct contact with a rocky mantle. This is the crucial detail. Water touching rock, heated by tidal friction, creates the same hydrothermal vents we see on Earth. If you were to design a perfect incubator for extraterrestrial life, you would build Europa. We are no longer guessing. The upcoming Europa Clipper mission is on its way to scan this world in unprecedented detail, scouting landing sites for a future mission that will attempt the most ambitious engineering feat in human history. Landing on the ice, melting a hole, and releasing a drone into a black alien sea. The narrative of our solar system has shifted. We used to look for Earth-like planets, blue skies, green grass, warm sunlight. We thought life had to look like us. But the water worlds of the outer solar system suggest that life might prefer the dark. It suggests that while the surface of planets may be battered by radiation and asteroids, the safe havens are deep below, protected by miles of shielding ice. From the resource-rich shadows of the moon that will fuel our ships, to the crushing depths of Earth that teach us how to explore, to the warm, salty oceans of Europa and Enceladus, the path is clear. The water is there, the fuel is there, and the probability that we are the only living things swimming in these vast, hidden oceans is shrinking by the day. We just have to break the ice. If you want to stay updated on the missions that will define the next decade of space exploration, make sure you are subscribed. The universe is far wetter and far stranger than we ever imagined. Thanks for watching.